Last week I talked about the science of climate change and about scenarios of emissions. This week I'm going to talk about how to get rid of those emissions, right? Which naturally follows from the discussion on scenarios. And then next week Diego is going to take over and talk about how much that would cost, right? I will give hints today, but I won't talk about the costs per se. And then the week after it's about the instruments, what you would do as a policymaker. But today is about technical options. So this is where we are in the slide pack, right? The scenarios and abatement options are in one slide pack, but we're going to cut in here and we're going to talk about options for emission reduction. I'm going to return to the Kaya identity. So next week, or last week, even, I put up this identity, right? That emissions are equal to the number of people times per capita income times the energy intensity of the economy times the carbon intensity of the energy sector. And then P again cancels against P, Y against Y, X against X. So this is an identity, E equals E. Now, if this is true, and it is, then if you take the log on both sides of the equation, then it's still the same thing, right? Or it's still true. If E equals E, then log E equals log E. So the natural logarithm of emissions is equal to the natural logarithm of population plus, that's one thing that a log does, right? The natural logarithm of per capita income, the log of the energy intensity of the economy and the carbon intensity of the energy sector, right? Now, if this is true, then it's still true that if you take the first partial derivative to time on both sides of the equation, then that must be true as well, right? The change, if E equals E, then the change in E equals the change in E, right? So then we have this expression here, and you wonder, like, what does this mean? What is this for a strange thing? But then when you apply the chain rule, right, and you look at the first partial derivative of the log of E to time, first partial derivative of the log is 1 over E, right? So 1 over E times the change in E, right? The first partial derivative of E to time. Well, this is just how much emissions have changed, right? So one way to denote that is to put a dot over this, right? So this is the change in E, this is E itself. So this is nothing but the growth rate of emissions, right? So the Kaya identity implies that the growth rate of emissions is equal to the growth rate of the number of people plus the growth rate of per capita income plus the growth rate or the change in energy intensity plus the growth rate of the emission intensity or the carbon intensity, right? That just follows from the Kaya identity. So now we know how to get rid of emissions. Because there's essentially 4 options. What we want is, for emission reduction, is this thing should become negative, right? Emissions should fall, that means they should grow at a negative rate. There's 4 basic options to do this. You can reduce population growth, you can reduce income growth, you can reduce or accelerate the change in energy intensity, or you can accelerate the change in emission intensity. Those are your 4 basic options to reduce emission. And I will take them in turn, starting with population growth. So one way to get rid of emissions is to have fewer people around. This is a tricky option. Most, or at least many, democratically elected governments would go nowhere near how many children you guys would like to have, right? That is a taboo to talk about in many countries. It is changing a little bit. If you look at the Meloni government in Italy, for instance, it is actively promoting, and the same is true for the Orban regime in Hungary. They're actively promoting Hungarian and Italian women to have more babies. But typically this is not something that a polite politician or a smart politician would stand on and say, you guys should breed harder, right? It is different on the hard right. Another exception is the government of China. I do not understand why the test has to be done 5 minutes past 9 rather than 5 minutes to 9 when it would not disturb any lectures, right? And it would be just as effective to have a test 5 minutes before 9. So one exception is the government of China, which for a very long time has claimed in international climate negotiations that the one-child policy is their major contribution to international climate policy. Now that is complete nonsense. The one-child policy was introduced long before the Chinese government worried about climate change. It was introduced for completely different reasons than climate policy, but they've long made that claim. Actually, it's now the opposite, right? The Chinese government is very worried about climate change, and they have reversed the one-child policy, right? Rather unsuccessfully. I mean, the policy is no longer there, but Chinese women are not having many more babies than they used to have, right? So this is one option. It's not an option that is particularly effective or particularly popular. And of course, you recall the discussion that we had last term about the environmental movement and its attitude towards population growth, particularly the growth of population of people with a different skin color than the average European, right? So if you take population growth off the table, then let's talk about economic growth. A very effective way of reducing emissions. What you're looking at here are in blue, you're looking at the GDP of the countries of the former Soviet Union after 1990 and the former Soviet Union before 1990, or the Soviet Union before 1990. And in red, you're looking at their emissions of CO2. And what you see is that when the communist regime collapsed, the economy collapsed and it took emissions with it, right? So this is a very effective way of reducing emissions. It is again not something that any clever politician would stand on an election platform. We're going to crash the economy, right? I mean, sometimes politicians do crash the economy, Liz Truss being one example, but that was not her intention, right? Of course, everybody with half a brain had advised her that this is what would happen, right? But still, she believed that he was doing the right thing. So very effective, not something that is really in the instrument, in the book of instruments, right? You also notice what happened after, say, the year 2000 in the former Soviet Union, right? I mean, the economy recovered, but did not take emissions with it that fast, right? So we see here real decoupling of the economy and the environment going on in the former Soviet Union. And that is mainly because the heavy industry did not return, right, to Russia and other places, and that is why emissions did not grow nearly as fast as the economy recovered. So having taken two options off the table, basically, we are left with only two, right? And the important thing here to realize is that, well, if emissions are going to fall, but we can't really touch population and say that population continues to grow slightly, and that is the projections that I showed you last week, and if the economy is continuing to grow, if you want emissions to fall, then you need to work really hard on the other two, right? If economic growth is positive, but emissions growth have to be negative, then you have to work really hard on your energy savings and on your fuel switching. So let's look at the options for saving energy. There's essentially two, maybe three routes there. One is better technology, and the other is behavioral change. Now, let's start with technological change. What we have seen happening in the market, in any market we have looked at, for any period of time we have looked at, is that for a single product, if you compare them like with like, new models tend to be more efficient, energy efficient, not Pareto efficient, energy efficient than previous models. And the most famous example is from a paper by Bill Nordhaus, the Nobel laureate, where he reconstructed how much it costs to light a room. And you see the results here. It actually ends in the year 2000, starts in the year 1800. If you want to light a room with tallow candles, then the cost is gonna be, that must be almost 700. And it doesn't have a unit on. $700, I think, per lumen, but I'm not sure how many lumens you would get for this. And then over time, we switched to oil lamps, and then we switched to gas lamps and kerosene, the filaments, the fluorescent bulbs, and of course it stops in the year 2000. We don't have the LEDs here, which are cheaper still, right? And you can do this actually in the same paper. He goes all the way back to Babylonian times, and then it's an order of magnitude more expensive still. Also note that this is a logarithmic scale, right? So it's not a linear decline, it's cratering. And you can do this for any product for which you have data, essentially. You always find the same pattern. And the reason for this is very simple. Energy is a cost. So if their producer puts a new type of lighting on the market that produces the same amount of light for a lower cost, for a lower price, then you guys would want to buy it, right? Or vice versa, if somebody puts on the market a lamp that produces more light for the same price, then as a consumer you would want to buy it, right? Because energy is a cost, the market will always try to deliver cost savings, because then you can sell your product better, right? So if you compare like with like, you see this for everything that consumes, everything that uses energy, right? Which does not mean that energy efficiency necessarily improves, because sometimes this technological progress is diverted. And a clear example here is the fuel economy of cars on the US roads. The data starts in 1975, ends in the year. The data don't end in the year 2025. I think it's 2020, because we have the last observations. And this is fuel economy, right? So we flip the scale. So going up is good, going down is bad. And what you see indeed that in the second half of the 70s, the fuel economy improved, right? Energy efficiency improved, which is good. But then the trend reversed. And you can sort of conclude from this, well, what I just told you that this is true for every product on the market was a lie, right? No, that's not what is going on. So this is the fuel economy, which indeed went down, right? Cars consumed more petrol per mile traveled. But there's two other things going on. In blue, you're looking at the weight of the average car on the road, which went up a little bit, but still it went up. And then in yellow, you're looking at the power of the engine, which went up and up and up and up and up. And actually, if you compare these trends, then what you see is that actually a remarkable feat of engineering, particularly here, you see ever more powerful engines and still cars that are getting heavier. And at the same time, fuel economy is improving, right? And in this particular period, from 1985 to 2000, you see much heavier cars, much more powerful engines, and fuel economy only came down a little bit. So this is a major feat of engineering, right? That these American cars are pulling ever more weight, ever bigger cars, ever faster acceleration, and the fuel economy did not budge that much, right? So the engineering effort went into what Americans thought were better cars, bigger, faster, heavier, what have you. Not necessarily safer, right? Because these bigger vehicles have their point of gravity higher, so they roll over much more easily than other cars, but it sort of creates this sense of safety if you're sitting high above everybody else, right? Until everybody else gets a big car as well, right? And then of course, if you drive in a normal car, then you feel unsafe and you want to buy a big car as well, right? So these energy or these technological improvements do not necessarily go to reducing emissions, right? That's the important thing to keep in mind here. There is technological change, there is technological progress, but it may be that the customer wants something else than lower energy cost. There's also the so-called rebound effect. If a product becomes more energy efficient, then essentially you get more out of it for the same input. So essentially the price of the cost of using that particular technology falls, and then of course basic economic theory tells you we're gonna use more. Now there's been a whole bunch of studies of this, and we're going to stick to transport, and this is a meta-analysis, so an analysis of all the papers that have been published, trying to estimate the so-called rebound effect. And here you see the results. In blue, you're looking at the short-term response, and essentially what this says is that if energy efficiency improves by 10%, then energy use is going to fall by 9%. And the 1% difference between the two is people driving more, because it has become cheaper to drive, right? That is in the short run. In the long run, that actually goes up to 30%. So if energy efficiency improves, if fuel efficiency improves by 10%, then energy use will fall by 7% because people drive 3% more, right? That is the rebound effect. So yes, this technological change does not necessarily translate, in this case, translates fully into emissions falling. Another option to improve, staying with transport, to improve energy efficiency is to shift to other types of transport. And last term we talked about cycling. There's of course other options as well. Just per passenger kilometer traveled, public transport is much more efficient than private transport. Essentially because you pack more people in a vehicle. Yes, that is a bigger vehicle, but there's many more people in, right? I mean, I drive to work in a pretty big family car on my own, so I'm carrying all that steel and aluminium with me, which is just very inefficient. Right, I should have taken the bus if there had been a bus, right, from where I live to where I work. And of course, walking and cycling use even less energy per passenger kilometer. This is a funny picture. This is the advertisement for the Eurotunnel. This is a prediction of what the European rail network will look like in 1993, right? They were just opening or working on HS1. Saying, well, this will be HS2 and 3 and 4, and then this didn't come quite as true as they said it would. For instance, the direct line from Amsterdam to Hamburg is still not there, right? All the stuff in the UK. But it is definitely an option, right? And in countries like France, we actually do see a major shift. We have seen a major shift from domestic flights to fast trains, right? Done all these points, right? Talked about rebound effect, modal shift. Let's look at another way of saving energy. If you ask any engineer, they will tell you that a lot of energy serves no useful purpose. And here we see an estimate of that for the United States. It's not quite a fair picture. This is the energy that's going in. I believe the year is 2017. Yes. And this is the energy that actually serves a useful purpose, and what remains then is the energy that they call rejected energy, that is essentially waste, right? What you see is that this is 2/3 and this is 1/3 of total energy. It's not quite fair what they do. So a lot of energy is actually lost in power generation. So if you're burning natural gas to make electricity, you don't just make steam that drives a turbine, and then the turning of the turbine actually makes the electricity, right? You also generate a lot of heat, and most of that heat is just dumped, some in the atmosphere, some into cooling water, right, back into the river. Same if you're burning coal for making electricity. And actually, power generation, thermal power generation, you need about 3 times as much energy, 2 times as much energy goes in, as 3 times as much energy goes in as comes out. So that is essentially a waste, right? And that is why people are using combined heat and power plants, so that we can use the heat usefully. If you want to see a combined heat and power plant, you need to look outside the window, right? But they buried it. It used to be above ground, now it's underground, but it's there next to Fulton. So that is going on, right? And this picture is unfair because here they start with petroleum, right? Rather than add the transformation of crude oil to petroleum. It actually also takes a lot of energy. and energy gets lost there, but for some reason they didn't include that. But also what we have is in the final energy use, residential, commercial, industrial, transportation, a lot of energy is wasted in the sense that it does not serve any useful purpose. And in the residential sector, that is about 30%. And these are such things as leaving the lights on in the bathroom. These are such things as making a cup of tea and boiling a full kettle of water, even if you only need 1 cup of water, right? That sort of stuff. In the commercial sector, it is leaving the lights on after closing hours, as you see many shops do. Walk around campus, if you walk around any office complex, what you see is that there's lights on even though everybody has gone home. Right? That is energy use that serves no useful purpose, or at least it does not seem to offer any direct use to anybody. And if you can get rid of that, and if it's truly 30% or maybe even 60% of energy use, then of course you also cut emissions immediately, right? So that is an option that people talk about. But the question is, how are you gonna do that? Because a lot of this is essentially habituation, people doing things that they have always done, and now you tell them that you should stop doing that, which is difficult. People are difficult to convince. And this is an illustration, another meta-analysis of a whole bunch of papers where they looked at so-called nudges, where the utility company sends you a letter saying you consume more electricity than your neighbors, or the electricity company sends you a letter and say your electricity use has gone up by 5% last month. Is this really what you want to do, right? So it's sort of like this soft way of trying to convince people to change their behavior. There's been experiments with handing out sort of devices for people to hang in their shower, and then it starts beeping if you've been in the shower for more than 3 minutes, right? Because that is according to engineers, the optimal time that you should stay in the shower. It's enough to clean yourself, but most people want to stay a little bit longer. Those sort of things, or hotels encouraging you to take a shower with somebody else, right? Even if you are there on business on your own, they would still encourage you to do this. Now, and this is then how effective are these measures, right? And what you see is that, yeah, a lot of studies show sort of effects in the short run, that people respond to these things, but it's not impressive, right? I mean, energy use falls by a little bit. Also, what these studies find is that you sort of have an initial effect, and then it very quickly peters out, that a few weeks after, people are back to their old habits. The assumption is often that these things come at no cost, that we can avoid wasting energy, and that would just save money because we no longer have to pay for the energy that we no longer use. But I think that isn't quite true. One issue is that this is a form of social control and social pressure, right? And most of you live in shared accommodation, right? You share a house with other people. And you may live with an energy Nazi, right? Who keeps nagging you that you should not boil so much water and that you should turn off the lights, right? And yes, there is no monetary transaction there, but these people are particularly annoying, right? And it creates all sorts of tensions, and that is a real cost, right? So it is not exactly costless to do these things, and it's not particularly effective. There are deeper problems, and that is what an economist would call a principal-agent problem, where the agent is the one who controls the resource, who makes the decisions about the electricity use, say, and the principal is the one who pays for this. And if those two people are different people, then it's not necessarily the case that their incentives are aligned, right? And here we're looking at an example. This is from Wales 3 years ago. And the question is your loft insulated? Are your cavities insulated? The cavities of your house. The walls insulated, and do you have solar power, right? It's all renewables, but it's basically solar, or a little bit of biomass as well. And if we compare owner-occupied to private rented, then what you see is that the rented ones are doing systematically worse than the owner-occupied houses. And the reason for that is a principal-agent problem. So most of you, I guess, are in rented accommodation. If you look at your contract, if you look at your lease, you are not allowed to put in double-glazed windows, right? You are not allowed to put in cavity wall insulation. That is the landlord's responsibility, or the landlady's, right? But you are the one who's paying for the heating, right? So it is in your interest to insulate your home, because that would reduce your energy bill, but you are not allowed to touch this, right? Now, you may think it is in the landlord's or the landlady's interest to insulate your home, the place where you live. But actually, if you look at the rental market and the rents that people can charge and relate that to the energy properties of the house, whether it's well insulated or not, then that cost saving in energy is not fully translated into higher rents. Well, it simply means that the one who can make decisions does not have the full incentive to actually make this investment, right? Similarly, if we are talking about electricity use on campus, right? I am the agent. It is my responsibility to turn off the lights after the lecture. But I don't pay the electricity bill, right? The Vice Chancellor does. And if I am a good boy and I turn off the lights and I turn off the computers every time after a lecture, then you say that's a small effort, right? But I'm running 2 other meetings, right? And I'm doing other things. I don't get a raise in my salary. I don't get an increase in my research budget. So why would I bother, right? Now, solving principal-agent problems is a pastime of economists, particularly people in industrial organization. This is one thing they love to do, right? It's a very interesting problem, how do you design a contract so that incentives are aligned, right? So that's very interesting, lots of very interesting theory. But going back to this example of me turning off the lights after the lecture is over, essentially what would need to be done is that my contract specifies that I pay for the electricity, right? That I have an electricity account And presumably I would need to swipe a card whenever I walk into a room, and this is now the electricity that I pay for, and I have to swipe the card again if I leave the room. And you can see that it's technically feasible, right? And then you can sort of like say we're going to give everybody in the university an electricity account, and the people who use too much electricity sort of get deducted either in their salary or in their expenses accounts in some way or another. But you can immediately see that this is technically a little bit challenging for a university that is not particularly good at delivering technology, right? I mean, all our forms are still in Word for some reason. So you can sort of imagine that this university is not capable of delivering this technically, but it also is an immediate affront to labor relations, right? You're putting an additional task on us, and so on and so forth, and you can immediately see that the unions, who are already very agitated about all sorts of things, would get very cross about it, right? So it's not going to happen anytime soon, right? I mean, the solution is there in principle, but it's not necessarily there in practice. So these things, yes, they are there, can be done, but it's not easy. The final thing you can do is say use less energy. So for those of you who have seen An Inconvenient Truth by Al Gore, it ends with you should put on a sweater, right? And that is Al Gore's solution to the climate problem. Wear a sweater when it's cold rather than turn up the heating. That is a hard message to sell, right? Because people like to walk around their house in their underwear rather than fully clothed, right? Another way of saving energy is to convince people that a holiday in Bristol is just as exciting as a holiday in Bangkok, right? And yes, you would use much less energy if you would holiday in Bristol rather than in Bangkok, but it's not quite the same, right? So trying to convince people to economize on what many people consider a luxury is actually very, very difficult. This appeals to a small minority of people, but not to a large number. And I mean, last week there was this survey came out of people in France who where I believe 48% of people under 40 said that it would be a good idea to limit air travel to 4 flights in a lifetime. Not 4 flights per year. 4 flights per week is getting a little bit much. I've been there, it's not good for you. I think that is just young idealists speaking, people who do not really understand life, right? People who have no aspiration to ever work for an international company, for a multinational company, where you would be flying that amount per month, probably, rather than per life. Also people who have no relations abroad, right? No friends abroad, no family abroad, don't study abroad, right? This is very xenophobic, right? If you say, well, you can't fly that much, then essentially what you say is you should stay within 500 kilometers of the place where you were born, right? This is just not an option. But there are definitely people who are willing to give up this sort of stuff. But I don't think they will ever take the majority with them. I may be wrong, but I don't think I am. So this was the third part of the Kai identity, right? Saving energy. Yes, there is potential there. Yes, it can be done. Yes, the market will work with you to an extent. But don't think that this is an easy solution or a solution that will necessarily bring a whole lot. So the next thing you can do is change the carbon intensity of the energy sector, right? Switch fuels. And essentially what we want to do is move away from the fossil fuels, oil, gas and coal, to carbon neutral or low carbon types of energy. There's nuclear, there's hydro, there's wind, there's solar, there's biomass. All these options are there. There's a few more options. All of these are by now proven technologies. So there's no technological challenge. Well, there's technological hiccups to be solved, but they're proven technologies. Some of them long proven, some more recent. If you look at the energy balances, then the potential of nuclear, hydro, wind, solar and biomass combined is enough to supply the world's energy needs 10 times over or more. It's not that there's no major technical challenges, and there's also no physical constraints there. There is enough carbon neutral energy out there to supply any energy need that you can imagine. An important thing here to realize is that this has to be done anyway. So this is a complicated picture with lots of messages. And unfortunately data that is a little bit old, but this is from the United States Geological Survey, and I don't know what they've been doing, but they haven't updated this for the last 10 years. So what you're looking at here, right, is on this axis you're looking at different types of fossil fuels, shale gas, natural gas, so these are the gases, this is the liquids, different types of oil, and then at the bottom you have 3 types of solid fuels, coals, lignite, and so on and so forth. So that is the simple thing. Then you have different colors: reserves, proved, probable, possible. Right? So reserves are those things that we know are in the ground and we know how to get them out of the ground at a profit. Right? That is a reserve. Then proved is stuff that we know is in the ground, but we don't quite know yet how to get it out at a profit, right? Then we have probable reserves. You sort of suspect that it's there, but we haven't quite looked hard enough. And possible, yeah, it might be there, right? So that is what the grayscale means. And then on the horizontal axis, we have the most difficult one to understand. What if we take this stuff and burn it all in one go? How much would we add to the CO2 in the atmosphere, right? This is not a wise decision to burn all your coal in one go, because it would suck all the oxygen out of the air and would not be good for us, and we would not know what to do with all that energy. But let's imagine that that is what we do, right? And then the scale of this axis is in parts per million by volume. And the way to look at this is essentially, well, if you want to sort of limit global warming to say 2.5 degrees, then perhaps we can emit another 100 or 150, or we can add another 100 or 150 parts per million to the atmospheric concentration, right? So that is what these numbers mean. Now, if you look at the reserves of natural gas and crude oil and you add them up, then you sort of get to that 100, 150 area, which means that we can burn all the gas in Russia and in Qatar, and we can burn all the oil in Saudi Arabia and Kuwait without warming the climate too much. That is actually not where the problem lies, right? The climate problem is found elsewhere. The climate problem is found in, once we start running out of natural gas, and we are quickly running out of natural gas, and once we start running out of our conventional oil from conventional places, and we're also running out of that, not quite as fast as we're running out of gas, what is going to replace that oil and gas? That really is the crux of the climate problem. And we have to find a replacement because the stuff is running out, right? Now, here comes the story of this data is 10 years old. USGS, please get your act together and update the numbers. The market has done, been a lot of development in shale gas, as you may have noticed, and there's been a lot of development in oil shale as well as in the extra heavy oils. And that is what the market has done. So an enormous investment in capital, as well as the reason that we now can get shale gas and shale oil. Shale oil is here actually, rather than here. This is oil shale, I'm talking about shale oil. Anyway, it doesn't matter. The market has bet very heavily, invested very heavily in the shale oil and gas, right? And not just a lot of money, but also a lot of brain power. Actually developing fracking is a major technological advance if you just look at it from an engineering perspective. This is actually a very hard thing to do, and we've now mastered that, right? So that is a worrying development for climate. Another worrying potential development for climate is that we could replace gas and oil with coal. Now, you may wonder how, right? And you may wonder, is that feasible? How would I drive a car on coal, right? Well, the Nazis had the same problem, right? When we blockaded Germany during World War II, they were running out of liquid fuels, and then they invented the so-called Fischer-Tropsch process that allows you to liquefy coal. And when we blocked the apartheid regime in South Africa, what they did was they refined the Fischer-Tropsch process and started liquefying coal. And there's a lot of coal in South Africa. And the Chinese army, which is very worried about the US Navy blockading the Straits of Malacca so that no oil can reach China by sea from the Middle East, has further perfected the liquefaction of coal, right? So yes, this is technically feasible. It's expensive, but there's plenty of coal around, right? So if it would ever come to this, the Chinese army will not stop for lack of liquid fuels, right? And if they can commercialize this, and that is still a bit off, this has only happened for military reasons so far and for sanctions and blockades, but if they can commercialize this, then there's so much coal out there. We can make the planet so incredibly hot if we burn all this coal. Another thing that people have been working on is the following, and you've all picked up on the concerns about fracking, right? And essentially what fracking is that they inject water at high pressure deep underground to push the gas out. And sometimes there's a little bit of chemicals in, but mostly it is water. But people in the UK are extremely scared of fracking, right? For no good reason. There's been so much fracking in the US without any major incident. But anyway, people are scared to death in this country about fracking. The Chinese at the moment are experimenting not with fracking, we're doing that as well, but with so-called underground coal gasification, which is a polite word of saying you take the coal that is underground and you set fire to it, right? And because it then gets combusted in an oxygen-poor environment, you produce lots of methane, right? As we talked about last week. And then you capture the gas that comes out. And yeah, injecting fire under your feet is a lot more scary, I would think, than injecting water under your feet. But that is what they're doing, and that is another way of getting this coal out of the ground, including getting coal out of the ground where it's actually very hard to mine. So if that is the solution, right, we're running out of oil, we're running out of gas faster. We need to find a solution to this. We need to find an alternative source of energy. If that alternative source of energy is a switch back to coal, then we are in deep, deep trouble in climate terms, right? Then we can make the planet like really, really hot. Then you're no longer talking about 2 degrees of warming or 3 degrees of warming, but you're talking about 6, 8, 10, 12 degrees of warming, right? So that is one way of looking at this particular graph. The other way of looking at this is that the politics around climate are all wrong, right? Because if it's not conventional oil and conventional gas that is the problem, then it's not ExxonMobil that is the problem, because they're running out of stuff anyway. It's not Kuwait that is the problem, or Saudi Arabia, or Russia. Russia is a problem in other senses of that word. It is what's going to replace this, right? So it's the unconventional oil and gas. It's Venezuela. It's Brazil. It's Australia that are really the problematic countries. It's Glencore that is the big bogeyman of climate rather than ExxonMobil, but that people do not realize. Now the third thing that comes out of this graph is it's actually very expensive and very disruptive to replace conventional oil and gas with something else. You need enormous technological progress, and I talked a little bit about the shale. You need enormous investments. So why not go for stuff that does not emit a lot of CO2? We need to make that investment anyway. ExxonMobil will not have the same business model as it does now in 20 years' time, because there is no gas anymore. And there's very little oil left, right? They will have to completely change their business anyway. And also, we will have to completely change the geopolitics of energy. Before my life is over, Saudi Arabia will no longer be a major player in the world energy market. Right? So we're gonna see the transition anyway, and all the instabilities that entails. So why not make that transition once towards renewables, rather than make it first towards unconventional oil and gas and coal, and then have to redo it again and switch to renewables, right? It's much easier to do it once rather than twice in short succession. I'm gonna break for 10 minutes, and then I'm gonna continue this discussion, and then we have time to move beyond Kaya as well. Okay, see you guys at 5 past. So, what can we do instead of fossil fuels? First two options, nuclear, hydro. Let's look at nuclear. This is nuclear power generation since essentially the start, right? We have a complete history of power generation. What you see is a rapid expansion early on, and then a decline, and now it's picking up again, particularly in Asia. In China, we see a rapid expansion of the nuclear fleet, a relatively rapid expansion of the nuclear fleet. Nuclear is a proven technology. It's almost carbon-free. There's a lot of concrete going in, but that's it. No issues with reserves or stuff like that, because we can switch to thorium if we run out of uranium. The issues are around public acceptance and cost. We actually do not know how much it costs to make electricity with nuclear power, because it's a state secret in many countries, and in other countries it's a commercial secret. We simply do not know. There are people who know inside the companies, but they won't tell us. So we don't know whether this is an economically good option or not. The issues with nuclear have to do with safety. This is mostly in the public mind. We all recall Chernobyl, we recall Fukushima. Fukushima had nothing to do with nuclear itself and everything to do with chaotic reaction of the Japanese government to a fairly unprecedented but not unanticipated situation. Whereas what happened in Chernobyl cannot happen with the current nuclear power plants, because they are inherently safe. You need to violate the laws of physics to make those things explode. So that won't happen. But it hasn't quite penetrated the public psyche yet. There are issues with nuclear waste. Again, this is mostly in the psyche of people rather than it's there in reality. There are nowadays safe ways of disposing nuclear waste for the next 10,000 years or so. But people are still very scared of this, and this adds to the cost. I used to live in Germany near the Gorleben. Transport would come almost by our house, and in order to move 1 kilogram of nuclear waste in Germany, what you need is a train and 10,000, 15,000 policemen to protect that train from protesters, which is enormously costly, right? As a result, German nuclear waste is stored in the stupidest place you can imagine, very near the nuclear reactor, in ways that are completely unsafe and unsanitary, rather than moving them to safe storage, right? So there are issues with nuclear waste, but again, there's a technical solution there. But because people are so afraid of this, there hasn't been much investment in new nuclear, as you can see, apart from in some authoritarian countries, particularly China. In Germany, in Europe, we have a very mixed picture. Some countries are building new nuclear: Finland, France, Belgium, and the UK. Other countries are closing down their nuclear power plants, particularly Germany, and are not going anywhere near building new ones, right? So it's a very mixed picture. And this is because the politics gets so very messy. Also in the US, you haven't seen any new nuclear for a long, long time. The thing to really worry about with nuclear, if you really want to make a dent in CO2 emissions, is that you need nuclear everywhere. You need to expand nuclear much faster than we have seen even in the heydays of new nuclear. And you would be building nuclear power plants in places where perhaps you would not want nuclear power plants to be in the first place. Because if you can build and operate a nuclear power plant, then you can also build at least a dirty bomb, but more likely also a real atom bomb, right? And in order to make a real dent in CO2 emissions, you would need to build nuclear in places like the Central African Republic or Mali, right? Where you just have terrorists roaming the countryside. And we've all got, hopefully, a little bit worried about the news that came out of Zaporizhia, right? Having a nuclear power plant in a war zone is just not a clever idea, right? Because things can go wrong, and drastically wrong, if you don't maintain it well. So nuclear, technically yes, politically, socially, no, don't count on it. Same is true for hydro. What you're looking at here in dark blue is the installed hydro, and in light blue the potential where there are the rivers and stuff and valleys to put more dams. Technically, this is one of the oldest renewable energy sources that are out there. It's fairly clean. There's again a lot of concrete going in the dam. There's methane coming out of the reservoirs, but it is much cleaner electricity compared to oil and coal and gas. But the issues here are again political more than technical or even economic. Hydropower is actually relatively cheap. And that is that, yeah, you can build a dam and that doesn't take a lot of space, but you then also fill up a reservoir, and that tends to take away essentially fertile river valleys, right? So that is where there's a lot of agriculture, often a lot of historical artifacts, because that is where the old civilizations used to cluster near the river, and you would need to displace a lot of people. So this is something that you can do in, again, autocratic countries, but democratic countries are very reluctant, and also getting funding for these sort of things from democratic countries through the World Bank is not easy. So I don't see a lot of potential for a major expansion of hydropower there either. And again, there are security risks here. And we've all seen what happened to the Nova Kakhovka dam in Ukraine, right? Which was not particularly pleasant. But that was a fairly minor dam with fairly minor ramifications. If the Three Gorges Dam goes, right, and some people are worried about the Three Gorges Dam, then you're talking about 10 million people dead, right? So there are risks like that. Over the High Aswan Dam in Egypt, there are always at least 2 fighter jets, because the Egyptians are rightfully scared of somebody blowing up that dam and killing a great many Egyptians, right? So there are security risks here as well. So nuclear and hydro, yes. Technically, yes. Politically, no. So that leaves other renewables, in way newer renewables, solar and wind, and I've been giving this course for longer than I care to remember. I used to say that this stuff was expensive. That is no longer the case. This is solar photovoltaics. The years are actually here. This is 1975, and it came from $100 per kilowatt hour. In 2018, it was less than 50 cents, right? That's a factor 200, right? It has come down rapidly. This picture ends in 2018. Progress hasn't stopped. Here we're looking at more recent data over the last decade. And for more renewables, here again we have the solar photovoltaics, right? You see the costs fall. Concentrated solar power has fallen as well. I'm a bit surprised by this number. Biomass is there, offshore wind, onshore wind. You also see a dramatic drop in the cost. The gray zone that you see here is the price of coal and gas fired electricity. And what you now see is that onshore wind is the cheapest way of making electricity. And solar is almost there, right? If you're building new power, if you're going to expand the capacity to generate electricity, then wind and solar are the cheapest way of doing so at the moment, or rather in 2020. And costs have come down, the price of oil and gas has gone up. Friends in China tell me that the only reason that they're still building coal-fired power plants, and they're still doing that, is because of political influence and lobbying, not because the economics make any sense. Right? Problem with solar and wind power is that the wind doesn't always blow and the sun doesn't always shine, so you need to store electricity. What we have seen is that the cost of storing electricity has come down dramatically as well. 1992, it was sort of stable for a while. Then what happened here is mobile phones and laptops. And then all of a sudden it became lucrative to invest in R&D, in better batteries, right? That is actually what's driving this. And then electric vehicles came along, and it has just come down and down and down and down and down. Again, dramatic, right? From 5,000 to 200 in the space of a few decades. That hasn't stopped. This picture stopped in 2016. But the costs have come down further. So that main problem of solar and wind, that it's non-dispatchable in jargon, is going away, right? Because it's so much cheaper nowadays to store electricity than it used to be. That also means that we can now switch away from burning petrol and diesel in cars. Electrification of light transport is now feasible. There's still issues there. There's still issues with range anxiety. A few months ago, I went to the United States, found out that my mobile phone didn't work and therefore my navigation system didn't work. So I had to rent the only car that came with a navigation system. It was an electric car, a fantastic drive, right? I could not make it from Dulles International Airport to Richmond and back, right? And not being experienced in charging electric cars, I can tell you that caused real range anxiety, right? Because I had the plane to catch. And I was worried that my battery would run out. This is still an issue, right? And sort of the nominal range that you get in an electric car is much, much different from the actual range in an electric car if you're also running a navigation system and the radio and your airco, right? But it is imaginable that within the next 10 years or so, indeed, electric cars will be really better than petrol cars. At the moment, electric cars are fantastic as a second car, but I would not recommend it as the only family car that you have. And there are issues there with safety. Essentially, part of the drop in the costs of batteries is because of ever greater density of the energy. You can store more and more electricity in essentially the same size battery, and that makes that these things become actually more and more bomb-like rather than battery-like. And we've seen that last night in Luton Airport, right, where an electric vehicle caught fire and took a parking garage with it, because there were other cars that were just as flammable next to it, right? So there are issues there, but they are gradually being solved. Because of the issues with energy density, heavy transport, and because simply there's not enough oomph in an electric engine, heavy transport, so that's ships, but as well as trucks, will probably switch to hydrogen rather than to electricity. Both electricity and hydrogen are not sources of energy, they are carriers of energy. That is, you need to burn coal to make electricity. So the electricity carries the energy to a useful purpose. The same is true for hydrogen. You need to spend energy to make hydrogen, and then you can burn the hydrogen. There's two reasons why hydrogen is probably the preferred option for heavy transport. One has to do with idiots like me. Hydrogen is much more explosive than petrol, so you would not want somebody like me to charge a hydrogen fueled vehicle, because chances are it will go boom if I do that, right? So that is one reason. Second reason is that you actually need a lot of space for hydrogen. I've driven in hydrogen fueled cars, I did not charge it, and essentially your entire trunk is taken up by the tank, right? This is fine if you use a car to drive around, but not if you actually want to go on holiday and pack a family into your car, because there's no stuff to put your bags, right? But of course, space limitations are much less of an issue if you're talking about a big ship or if you're talking about a big truck. And then the extra sort of the fact that you can store much more energy there actually favors hydrogen for heavy transport over electricity. Coming back to energy density, that is what is holding us up with aviation. Yes, there are now electric planes on the market, but typically they can carry a pilot and a passenger. And there's now one that can carry 4 people, but that's it. The idea that you can carry 300 people in a plane, an electric plane or a hydrogen plane for that matter, simply doesn't add up. Because the problem with batteries is that they're heavy, so you can stuff the plane with batteries, but the more batteries you put in, the further it goes, but also the heavier it becomes, so that is an issue. Whereas with hydrogen, it's the same issue that you need to store the hydrogen, but that is not enough. You actually need to compress it, so you need tanks with really thick walls, so that also adds to the weight of the plane. And at the moment, they're looking at it and saying, nothing beats kerosene, right? Nothing beats kerosene. For now, right? God knows what they will invent over the next 10 or 20 years. But all this is doable. Now, one solution for aviation, and I don't know why aviation is dropped here, is to switch to biofuels. And there again is technical potential there. So, what are biofuels? Essentially, the oldest fuel is wood, right? And for the last couple of thousands of years, people have also pressed seeds for oil and burned that, right? And that is, again, a proven technology. You could also dry dung and burn that. These things are all proven technologies. They are expensive, they are clumsy, but they are used in many places because it's the only fuel people have, but they're also increasingly used in as modern fuels, right? Going back to aviation, one of the problems with using biodiesel rather than kerosene, or bioethanol rather than kerosene, is that the energy density is again lower, around 8% for the best biofuels, which means that you need to have an oil tank that is 8% larger to fly the same distance, right? And in aviation, weight and space come at a huge premium, and that is why I'm not quite there yet. So that is the first generation of biofuels, and the Romans would recognize the things that we are currently doing, right? Which is burning wood. So what used to be the largest coal-fired power plant in the UK, Drax, has now switched to burning wood chips, essentially. And the technology is the same. Instead of feeding wood into the thing, you feed wood chips into the thing, and it burns just as well. Of course, the energy density of wood is lower, so you need to put more wood in. And of course, we don't have enough wood in the country, so we're importing it from the United States. But technically, this is a trivial thing to do. And as I said, the Romans, probably our ancestors 100,000 years ago, would recognize this. But also, and the other thing that we're doing is we're taking oil seeds and put pressure on, and then the oil drips out and we burn that, right? Again, this is a very old technology. The problem with these things is cost and convenience. So if you think of fossil fuels, what is that? It's plant material, essentially, right? It's very old plant material. that has been neatly compressed into coal by Mother Nature over a few million years, actually a little bit longer. We have essentially oil seeds that have been converted into oil by Mother Nature, into a liquid, and we just need to pump it out, or we have gas that Mother Nature has gasified for us. And that's all very neat, right? Now, if you take biofuels, that is essentially recent plant material. And then you would need to grow it, and then you would need somebody to collect it from the field, right? And then you would need to dry it, and you would need to transport it, and you would need to compress it, and so on and so forth. And all these things that Mother Nature has done for you with fossil fuels, most of the things, you would now have to do yourself, right? And you would need to hire somebody to do this for you. So that is why biofuels are so much more expensive, because a lot of the free labor is taken out of the equation. That we had the free labor that we had in fossil fuels. In both cases, it's just plant material, right? So the second generation of biofuels essentially make, I don't know why there's an S here, take this plant material and process it in a smarter way with better machines and so on and so forth. And there's a lot of process innovation that is going on there. And that drives down the cost of biofuels considerably. And I mean, I said that Romans would recognize some of our oil seeds, but Romans would not know, well, first they would not know about maize, but also they would not know how to get oil out of maize because it really comes in a low concentration, right? But that is actually the major fuel, liquid fuel in the US at the moment. It's corn diesel, essentially. Now the hope, but it's still, you would need to do what Mother Nature has done for you with fossil fuels, right? So it's still going to be always be more expensive. The thing that people put their hopes on, and I emphasize the word hope here, is the so-called third generation biofuels. And I think that is best understood if we look at brassicas. The potential is best understood if we look at brassicas. So this is wild mustard, right? Occurs naturally in the Middle East. And these things you see at the bottom is the same species, right? These are also brassicas. This is also mustard, essentially. Cauliflower, broccoli, kale, kohlrabi, you may not know that, Brussels sprouts and cabbage. It's all the same plant. The difference between this one and this one is 2,000 years of selective breeding. Now this is an annual, so we're talking about 2,000 generations of evolution. This is the potential for bioenergy. So what we have done for 2,000 years is completely change how plants look for food. We have not done the same thing for energy. Our energy crops are basically the same as they were 2,000 years ago. But our food crops have completely changed. Now, this process of the last 2,000 years of selective breeding was done by people who were using trial and error, by people who did not understand genetics, let alone genetic engineering, right? So this process that took 2,000 years for the brassicas can now be accelerated and probably compressed into 20 years if we know what we're doing, right? And there's been progress in the lab. Nothing has broken out into commercial applications yet, but there has been a lot of progress in the lab on making plants better for energy. And my favorite example are a new breed of algae. Essentially what you do, you put them in a vat of water, you leave it there for 2 weeks, and then there is a film of biodiesel at the top of the vat, and you scoop it out and stick it in your car and drive away. That is where we are going. There's a lot of progress in research in this field, but as I said, nothing has broken into commercial or anywhere near a commercial application yet. There's been some demonstration projects, but that's basically it. But you can expect enormous technological progress there, right? So give it 20 years and we'll have a solid supply of bioenergy that we can fly planes on without emitting CO2 on net, right? So that leaves me 15 minutes. Last week I talked about the chi identity and how you could use that to understand past trends in emissions and how you could use it to construct scenarios. I use the chi identity to classify 4 broad groups of greenhouse gas emission reduction. Only talking about CO2, by the way. There are other options and I'm gonna talk briefly about them. Last week I said that one source of CO2 emissions is deforestation, where essentially we replaced trees with grass. Grass is much smaller, therefore stores less carbon. If you burn a forest and let grass grow to graze your animals on, you release CO2 into the atmosphere, right? So slowing deforestation reduces CO2 emissions. Problem is that we don't quite know how to slow down deforestation because we have been trying this for a while now because people have been concerned about loss of biodiversity, loss of forest and so on and so forth. And it turns out that this is a very difficult problem, mostly because the people on the ground simply are not interested in, simply do not share the same interest that we do, right? We would like the people in Brazil to preserve the Amazon forest, and we would like the people in Indonesia to preserve the forest of Borneo, and we would like the people in Congo not to cut down their forest, but they have different incentives, right? They have kids to feed and so on and so forth, and often this is the only way to do so. So yes, slowing deforestation is an option, but it has proved to be a very difficult option to realize in reality. What we have seen is the reverse in North America and Europe. Because we are becoming so very good at growing food, we actually would grow too much, and therefore what we have been doing is taking land out of agricultural production. And in some cases this is just neglect, right? If you neglect a piece of land in Europe, then a forest will emerge, right? The same is true for North America. And in some places it's an active management of trying to recreate the forest as they used to be. And this is actually taking up quite a substantial amount of CO2 in these continents, right? And if you could accelerate that progress, then we take CO2 out of the atmosphere and store it in the form of trees, which is, most people like to look at trees, right? Another option is to take the CO2 out of the flue gas. So you have a coal-fired power plant, a pipe coming out with lots of CO2, and what you can do is take that pipe and remove the CO2 and stick it somewhere. Now this is a proven technology. We know how to separate CO2 from a flue gas. We know what to do with that CO2. We can stick it in soda or beer. The bubbles in your beer are CO2. We can stick it in greenhouses to make plants grow faster. And we can also pump it back into the ground in oil wells to increase the pressure and make the oil come out faster, right? So this is a proven technology. We know how to separate CO2 and we know how to transport it and stick it somewhere, right? The problem with this option is that this market is essentially saturated. So yeah, we know how to do it, but it doesn't mean that we have a reason to do it. If you want to make a serious dent in your CO2 emissions through carbon capture and storage, you need a very large infrastructure investment. because CO2 is less dense than methane, natural gas. MIT engineers reckon that if you really want to do this at scale, then you would need pipelines and everything that are around 5 times as large, 5 times as many as the pipelines that we currently have to transport gas. That's a serious amount of steel and concrete, right? So that is an issue. Another issue is that if you take an existing coal-fired power plant and you want to add a CO2 capture plant to it, actually it doesn't quite work because it's sort of the plant is misdesigned for this purpose and the pipes are in the wrong place and everything. So retrofit is expensive. If you want to really do it at a new coal-fired power plant, then it's actually much easier. Easier, not necessarily easy, not necessarily cheap. So people reckon that if you add a coal capture plant to a coal-fired power plant, then you will need about 25% more capital, right? That's a considerable cost. And about a third of the energy would be diverted to capturing the CO2, right? So you have a plant that is 25% more expensive and produces a third less electricity. This is not cheap, right? And then the other problem is that then you have all that CO2 and where are you going to stick it, right? What are you going to do with it? And there are suggestions there, but they are not necessarily popular. More than a few years ago, there was an accident in Nigeria where because of a small earthquake, a lot of CO2 was released over a village. Now we need oxygen to breathe, and because of that burp of CO2, 1,700 people lost their lives, and many more cattle. And the reason is, well, CO2 disperses quite quickly, but if you have a large emission of CO2 in one go, then essentially you have no oxygen to breathe. And then the winds come in and sort of disperse the CO2 in the next 20 minutes or so, but 20 minutes without oxygen is a bit too much for us, right? So this is an issue, right? So you want to stick that CO2 in some place where it won't burp out, right? Because that's a safety issue. Also, it completely defies the purpose because it's back in the atmosphere again, right? And that is a problem, not just objectively, that you need to find reservoirs that are stable and safe, but also subjectively. So in the Netherlands, engineers found a very good reservoir for CO2, and the engineers say this is perfect place to CO2, and all the geologists say this is a perfect place to store CO2. And then the government said, okay, we're going to do this as a trial. And that perfect place was right under the city of Rotterdam. And then the people of Rotterdam, who had been told for 20 years that CO2 is dangerous and we should not stick it in the atmosphere, now the government came along and said, we're going to stick the CO2 under your ground and it's perfectly safe. The people in Rotterdam said, no, I don't believe you, right? That this is truly safe. So there's also issues of political acceptance here, right? And then you can say, we're going to stick the CO2 somewhere deep in a nature reserve. And then, of course, you have a group of Boy Scouts and Girl Scouts coming and saying, yeah, we want to hike there, right? So yes, there are real issues here with safety and public acceptance. Technically, it can be done. Which leads me to 6 minutes for geoengineering. And there's been all sorts of options, all sorts of suggestions made for geoengineering. I'm going to talk about two. Essentially what you do in geoengineering is you change the climate back. Right? So the problem with CO2 and other greenhouse gases is that it changes the climate. And with geoengineering you essentially say we're gonna change it back to the way it was, or perhaps to the way we liked it. And this is sort of like the geophysicist's wet dream, right? Think of all sorts of fancy solutions that would work there. The most popular one is probably putting dust in the atmosphere. So we know that occasionally a volcano goes off and spews lots and lots of particles into the atmosphere, and then it gets cold, right? We know that, right? We also know that a lot of the coal that we burn put particles in the atmosphere and also cooled the place down. And I showed that last week. Those were the aerosols. So why not do that, right? In this particular illustration from balloons, in other proposals, it is done with airliners. And this is effective. It is also cheap. The most popular substance is sulfur. And because of acidification policy, we remove sulfur from the flue gas of coal-fired power plants, and as a result we have heaps and heaps and heaps of sulfur lying around and we don't know what to do with it. So people would actually pay you to take the sulfur off your hands. And then calculations show that if you have 4 aeroplanes, 4 747s is enough to take 2 degrees, take the temperature of the planet 2 degrees down, right? So yes, that costs money, right? But we're talking about tens of millions rather than tens of billions that other proposals would cost, as Diego will tell you next week. So they're cheap, right? Why not do it? Why not do it is perhaps better illustrated with the other proposal that takes physicists' fancy, and that is to put mirrors in space. I'm going too fast. Yeah, here we are. So, not drawn to scale. Sun sends lots of energy out into outer space. Some of it reaches us. If you draw a line from the top of the sun to the bottom of planet Earth, and another line from the bottom of the sun to the top of planet Earth, you would find that actually all the solar energy that reaches us goes through a fairly small part in space. So if you put a mirror there that reflects part of that sunlight, it will get colder, right? Now, that is not what is done here. Here the mirror is put in the L1 point. And the good thing about the L1 point is then the mirror is there and it stays there because it's sort of balanced by the gravity of the planet and the sun. And then you don't need to correct it, it will just stay put, right? And then you need a slightly bigger area. This area here is a few tens of square kilometers large. It's a pretty small area. So you don't need a big mirror. You can do this, right? And this will cost $500 million, maybe $1 billion, right? Pretty cheap solution. So why not do this, right? The big question here is, of course, who can do this, right? At the moment, probably only the United States. China is getting there, right? Can probably do it in 10 years' time. And then the question is, who controls this, right? And if President Biden is in charge of this mirror, we feel fine, right? Because he's an innocent old man, mostly. Or at least he creates the image of being innocent. Donald Trump were in charge of the mirror. Would you sleep safely and soundly? If Xi Jinping were in charge of the mirror, would you feel safe? So that is the big problem with geoengineering. It can be done, it is cheap. Some of these proposals are so simple that an organization like Hamas could do it. It is very scary, right? if all our politicians and all the people in power were sensible and nice, then I would say go for it. And we have some sort of way of democratically controlling what would be done with this technology, then I would say, yeah, this is a no-brainer. But that is unfortunately not the world in which we live, right? And of course, there's the big issue with the uncertainty, right? There have been experiments with geoengineering in the past. One example is the Soviets diverting water from the Arctic Ocean to the south, which caused the famine in China, rather than created opportunities to grow cotton. We have the Greek colonial regime trying to create rain over Athens, which caused, it did create rain, it caused major floods in Turkey, right? One thing that I told you last week is that the climate system is actually very, very complex. And we don't fully understand it. So the idea that we could go in and change the climate back and we would somehow be able to predict what the results are, I think is a bit over-optimistic about the state of knowledge about these things. But of course, that would not stop some people from trying, right? So it is definitely something that we should understand, but it's perhaps not something that we should put our hopes, our faith in. That's all for me this week. Next week you have Diego for the next 2 weeks. I'll be back in week 5 for more sciencey stuff, but then about the impacts of climate change. Okay, I see you guys then.